So in the last class, we had ended the class with UDP, right? So we had learned that what are the different properties or features of UDP, and then we had learned that what is the way in which some errors are detected in case of UDP. Okay, so even though it is not a reliable data transfer protocol, it still provides a way of just finding out that whether there is an error or not. Okay, so we had ended our class yesterday on that one. Today we are going to talk about reliable data transfer. Okay, so some principles of reliable data transfer, which will basically tell you that what are the different types of function that you would need to write both at the sender side as well as on the receiver side, so that you can ensure that reliable data transfer is happening between these two entities. Okay, why do we need the reliable data transfer? We already know that there can be a lot of packet loss, there can be a lot of errors that can happen, and the channel through which you are actually transferring the data, that is not a reliable transfer channel. So in that case, somehow, because we are telling the customer that I will provide you reliability while your data is being transmitted. So in order to ensure that, we need to write these small functions. We need to see that what are the functions that are actually there, that should be there both at the sender side as well as at the receiver side. All right. Okay. So as I already mentioned, that see, this is an abstraction of what is happening. Okay, so at the sender side, you have the data. This is at the application layer. You send it to the transport layer. So in this chapter, what we are doing logical transfer of data from transport layer of one sender to transport layer of another receiver, right? So we are not looking at what is going on in the lower layers right now. Okay. So just the logical transfer of data from the application layer, then from the transport layer through the reliable channel to the receiver's transport layer. Here it is. And then after that, extraction of data, and then to the sending it to the application layer of the receiver process. Okay, so this is just an abstraction of what happens at the transport layer of these two entities. Okay, now what is the reality? Okay, the reality is that your channel is going to be unreliable. Okay, so if channel is unreliable, we need to have reliable service implementation. Okay, because we have promised the customer that I'm going to provide you reliable service. So if you have already promised the customer that you will provide the reliable service, so therefore you need to have certain protocols that need to be followed both at the sender side as well as at the receiver side, just to find out that what can be the different cases which basically will tell you that which are basically examples of unreliability in the channel. With all those different cases, since you have to handle all those different cases, you have to write functions corresponding to those. Okay. Now there are several challenges even to this, right? So we will see what are those challenges. But first, let us see what's happening in this diagram. So you have the sending process here. The data is being sent from the application layer to the transport layer, where you have the sender side reliable data transfer protocols. Okay, that means a set of rules or a set of functions that are there at this side. Now from here again, you send it below to the network layer and so on, and then through the reliable and unreliable channel, it passes on to the receiver process. Okay. Of course, the packet that is received, you decapsulate it, get to the transport layer where you have the receiver side of reliable data transfer protocol. So that means a set of functions that you need to implement in order to check that whether the data that has been received is a reliable data or not. That means it is a correct data or not. And then if you find that okay, it is correct, send the data to the application layer, okay, at the receiving process, corresponding receiving process that we have already studied in the last class using sockets. Okay, so you have the different identifications. How do you identify the sockets, whether it is while using TCP or while using UDP? And then correspondingly, using demultiplexing, you send the data to the corresponding socket, okay, through the corresponding socket to the application layer process. Okay, now, right, so what is the problem that can happen here? Okay, so the complexity of these reliable data transfer protocols, both at the sender side as well as the receiver side, that will depend on the characteristic of the channel through which you are transferring the data. Of course, if the channel is very reliable, then most of the times there is no loss, or data will not get corrupted, or the sequencing of data will not change. Okay, so if your channel is that great, then it's fine. Then your data transfer protocol may not be that strong. But if it is not that, if the channel is highly unreliable, in that case you will have to create more complex data transfer protocols. Okay. Now, what is the challenge? So first thing that we got to know is that depending upon the unreliability of the channel, the complexity of the protocols is going to change. Now, suppose you still know these facts, okay, that whether the channel is reliable or unreliable. But what is the biggest challenge is that these two entities, the sender and the receiver, they actually do not have any contact with each other. They do not basically know anything about each other. Okay, so it's basically kind of a curtain, right? So it's like closed. Sender also does not know what's the receiver status. Receiver also does not know what's the sender status. Okay, so you are sending a packet from sender to receiver. Sender knows only that he has sent the packet. Okay, he does not know that whether the packet has been sent to the receiver or has been received at the receiver's side or not. Okay, and when the receiver receives one packet, first of all, he does not know that whether the packet that has been sent is actually a correct packet or not, which was originally sent by the sender. Okay, so there has to be some way in which these messages need to be communicated. That is, the sender must know that the receiver has received the packet, and the receiver must know that whatever packet the sender has sent it, or whatever packet the receiver has currently received via this unreliable channel, that packet is actually the correct packet that was actually sent by the sender process. Okay, so these are the complexities that are there in case of reliable data transfer. So for that reason, we need to have some way of communicating these information via messages. Okay, all right. So how do we need to, or how would we find out that whether there is the data has been actually received at the receiver side or not? So what we do is as I told you, that we will write a set of functions or a set of rules which will be basically part of the reliable data transfer protocol at the sender side and at the receiver side also. Okay, so first we will start with the easiest case. Okay, so but here first let us see that this is the same thing that I was talking about, that this is the sender process. So you just write a function RDT send. That means you are sending the data from the application layer to the transport layer. Okay, in the transport layer you have the sender side implementation of the reliable data transfer protocol or the RDT protocol, and then you have the UDT. UDT send, okay, unreliable data transfer, okay, that is the header and the data through this unreliable channel. Then you receive it at the receiver's end, RDT receive. The data is having header and data here. Here at the transport layer, you have a receiver side implementation of the reliable data transfer protocol. Then finally, you extract the data and then using this function deliver underscore data, you deliver the data to the corresponding application layer process at the receiver side. Okay, so this is what essentially we are going to do. All right. So yeah, I have talked about it. Let me move. Okay, so this is basically a bidirectional communication over this unreliable channel. Now, so what are we going to do in this class? All right. So we are going to talk about, or we are going to see how a reliable data transfer protocol is actually developed. Okay. So first is we are going to incrementally develop sender and receiver sides of reliable data transfer protocols. Okay. So we are, for now, we are going to consider unidirectional data transfer. Okay. But we control the information flow in, so that basically control the information that will flow in both the directions. Okay. So basically just look at this. We are going to use FSMs for this. So at state 1, okay, so this state is basically going to be uniquely defined by any event or action that is being, any event, okay. Now, depending upon the action that is taken, you transition to the other state, right? That's what we know about an FSM also. So this is your state 1. So we will represent it as, okay, when we are talking about, the action that leads to a transition from state 1 to state 2, we will write it like this. That is, first one will be the event causing state transition, and below it will be the action that was taken or that needs to be taken for the state transition. Okay, so this is what the first part is. Okay, and this state is basically, so basically what is happening, this side will be the event and this side will be the action that is taken just to move to the next state. Okay, so just remember this way of representation. We will look at different cases now. Okay, so first case is your RDT 1.0 first protocol, and it is the easiest one, and it is basically reliable data transfer over a reliable channel. Okay, so what do we mean by a reliable channel and why it is called the easiest one? Because reliable channel is the one where you do not have any bit errors or no loss of packets. Okay, so basically it is an ideal kind of a situation. Okay, so we are currently, so I said, right, that we are basically incrementally seeing making the sender side and receiver side with different cases, right? So this is the first case. We start with the easiest one and use the perfectly reliable channel for this. Okay, so we will prepare separate FSMs for both the sender as well as receiver. Okay. So the sender will basically send data to the underlying channel and the receiver will receive or read the data from the underlying channel. All right. So now this is the sender side. So the first state is wait for call from above. That means from the application layer, there should be a call for sending the data, right? Sending the data to the transport layer, because there only we have our reliable data transfer protocols, right? So this is what's happening. You call this reliable data transfer send data, this one, and what's the action being taken correspondingly? The packet is being made with the data that you have received from the application layer, and then the packet is being sent. Okay, using this function UDT send packet. Okay, now what do we know? We know that a sender just simply sends a packet. Okay, there's no other task that the sender does. All right, and because the channel is reliable, you know, or the sender knows that if I'm sending the packet, then it will probably reach the receiver, okay, without any errors or without any packet loss. Okay, so there's only one task for the sender, just to make the packet and then send it over the medium. So that's why the corresponding FSM as has been given here. Okay, now we'll see the receiver side. So receiver side will also be the same thing, right? Only differences we are decapsulating. So from here the call will be, so at this point the call will be from the below layer, right? So wait for call from below. What will happen? You will receive a packet, okay, using this RDT receive packet, and what are the actions being taken? You extract the packet, extract the data from the packet as has been given here, extract packet comma data, and then deliver the data correspondingly to the application layer. Okay? So receiver also does not have any further tasks except from receiving the packet. Okay. So this is what happens in the unreliable channel, and we know that how to make a corresponding FSM for this. All right. Now, so yeah, as I already told you that this is the easiest one. Now we'll increase the complexities one by one. Okay. So the next one is RDT 2.0, right? So here we have the underlying channel which is having only bit errors. Okay. So there is a possibility that whatever data you are transmitting over this channel, the bits might get flipped. Okay. So you will have bit errors in this case. Okay. Now we have already studied in the last class that if we have bit errors, we can use checksum to actually find out that whether there has been any bit error or not. Okay. The problem is that after detection of errors, how do we overcome this? Okay, or how do we recover from it? You know that a packet was sent from sender to receiver, and that packet has error. Okay, so the receiver still did not receive the correct packet, right? So how do we go about it? Okay, so here it is, a question is asked that how do humans recover from errors during conversation? Okay, so how do we recover from it? Let's see. So we simply ask that, okay, whether you have received the correct packet or not. Okay, we just simply ask this question. If the receiver says that yes, I have received it, then only you know that okay, fine, your packet has been received, your communication has been uh, done properly. Okay, so the same idea is used here in RDT 2.0 with bit errors. Okay, so what do we use? We use this concept of acknowledgements. Okay, so what's this acknowledgement? So the receiver, so this is basically that the receiver will explicitly tell the sender that the packet that it received was okay. That means it was not having any errors. Okay, so this is the case where you know the packet was okay. What about the packet was not okay? So then you send a negative acknowledgement. Okay, so the receiver explicitly tells the sender that you know the packet that was received was having errors. Okay, so this is how the sender will get to know that whether the receiver received the correct packet or the incorrect packet. So once the receiver receives the incorrect packet, the sender has to do something about it. What it will do? It will simply retransmit the packet if it receives a negative acknowledgement or a NAC. Okay. So I'll call the acknowledgements as ACK packets and negative acknowledgements as NACK packets. Okay. Okay. So basically, what's the concept that's been used here? That means the sender sends a packet and then it waits for an acknowledgement from the receiver side. Okay. Well, whatever it may be an acknowledgement or a negative acknowledgement, but it will wait for a response from the receiver side. Okay. So let's see the corresponding FSMs for this one. So here now look at the states for the sender. Okay. So in the previous one, when we were looking at RDT 1.0, because the channel was perfect, that means the channel was reliable, the sender only had one task, that is wait for call from above and then send the packet. Okay, that's it. But now the sender also has to wait for any response from the receiver side after it actually sends the packet. Okay, so that means we have two states now, that is for the sender, that is wait for call from above, that means from the application layer for the data to be transferred to the transport layer, and then you have another state, that is wait for ACK or NACK packets. So let's see what are the corresponding functions. So here it is. So wait for call from above. What's the event? It is RDT send data. Okay. That means what are the actions that you need to take? That is make the packet, and the packet will have, now here remember we are basically trying to find out bit errors and we can do that with the help of checksum. So data will be there and in the header you will have the checksum field, so that you need to put before you send the data, and then use the UDT send function to send your packet. Okay. All right. So there's here uh, there's just a little error here. It will be send packet, not SNK packet. It will be SND packet. Just notice this. Okay, note this one. All right. Now, once the packet is sent, then what's the sender's job? We have already seen that here the sender is following stop and wait. That means it will send the packet and then it will wait for either an ACK packet or a NACK packet. Okay. So it will wait for it. Now, when it receives an ACK or NACK, then it will do a corresponding, it will act correspondingly, right? So now, if it receives a packet, that means the sender is receiving a packet, and that packet is actually an ACK packet. That means an acknowledgement from the receiver, that is that will tell that the received packet has been is the correct packet. So then no further actions are required. Okay. So no further actions are required. This is the event that has happened. That means an ACK packet has been received. So what will the sender do? Then the sender's task is just to wait for the application layer to send further data so that it can transmit again. Nothing else it has to do. Okay. Now what is the scenario when a negative acknowledgement packet is received? Okay. So you have received a packet. That means the sender has received a packet and the packet is unfortunately a NACK packet. Okay. So if this is true, then what do we have to do? Then as we know that the sender simply retransmits the packet. Okay. So the sender will retransmit it using this same UDT send packet. All right. So this is what will happen if you have bit errors uh, present in the data that was received at the receiver side. Now let's see what the receiver will do. Okay. So receiver's task here is that wait for call from below, right? So whenever it receives a packet, it will simply wait. So the receiver's task is to just receive a packet. Once it receives a packet, only then it will take some actions, right? So now we'll see what are the actions that it has to take. This is the state that the receiver is in. Now, if the receiver receives a packet and it is a corrupt packet, it finds out using checksum that it is actually a corrupt packet. So what it will do, it will send a negative acknowledgement. Okay, that's what is the receiver's task. Once it sends the negative acknowledgement, then again it will simply wait for some other packet to be received, right? So it will wait for call from below, right? So that's why it is coming back to this same state. Now what's next? Suppose what you received or what the receiver received is a not corrupt packet. That means it's a correct packet. Okay. So in that case, what are the tasks that are required to be done at the receiver side? The packet needs to be extracted. That means the data that is there in the packet, that needs to be extracted, and the data needs to be delivered to the application layer to the corresponding process. Okay, and once that is done, then you send acknowledgement to the sender. Okay, so these are the tasks that are getting carried out if the packet is not corrupt. Okay, extract, deliver, and then UDT send act. Okay, is this clear? If any doubts are there, you can ask question. Otherwise, I'll move forward. Okay, so I hope that this is clear.
Um, we know that the checksum is not a perfect guarantee, right? I mean, it can
Yes, it
fail.
is not a perfect guarantee. It may fail, yes. But for now,
In
we are just considering checksum as the just to find out bit errors. Okay, this is just, we are giving out what are the different functions that you can actually add at both these sides. Okay, you can always have a better version of checksum. Okay.
yes, ma'am.
Ma'am,
Yes.
does the receiver process the packet immediately after receiving it, or it may have delay in processing the packet?
It depends on how many packets are being received at the receiver side. Okay, in general the processing speed is much faster, okay, at any entity. Okay, but still if it is a very much congested scenario, you will see in, later in I think this chapter itself, okay, that if too many packets are actually coming, then of course there will be a delay. Okay.
Okay.
Excuse me, ma'am. Wanted to ask you, like, when, the corrupts, do they occur only during transmission, or once they've reached the receiver, like going through the layers, like, can some sort of corrupt happen there?
Okay, so we are currently assuming that there is only the error is only happening at the channel. Okay, the bit is getting flipped at the channel side. In general, it is considered that there is, when it is actually being decapsulated, you are not doing anything on the data. Okay, because the data is nicely secured within the frame, then within the datagram, then within the segment, right? So we generally assume that there's only problem at the transmission. Okay.
All right. Thank you, ma'am.
Yeah. Any other questions? Okay. If not, just give me a moment to drink some water. I'll continue after that. All right. So let's move on. Okay. Now there's a note here, right? That is whether the receiver get the message correctly. That state of the receiver is not known to the sender unless unless the receiver actually sends some information to the sender, which is why we had this ACK and MAC team. Okay, but for this entire procedure, we need to have a protocol. Okay, we'll see what can go wrong even if you have, the ACK and MAC packets. Okay, let's see. Okay, now first let us see what will happen if there are no bit errors for RDT 2.0. Okay, so the sender waits for a call from above. Okay? Once some data is there to be sent, so this is waiting for a call from above. So receiver is waiting for a call from the below layers. Alright. Now what would happen? These events will take place. That means RDT send data. That means the action taken is that you make the packet with corresponding checksum value and send the packet. Okay. Then what would happen? Then after this packet is sent, the packet is being sent over to the channel, and your sender gets into this state of wait for ACK or MAC. Okay. Now let's see what will happen here. So here we are considering that there are no errors, right? So data will be received at the receiver side. So data is received, and it is not a corrupt packet. Okay, so that means what are the tasks that are to be done by the receiver? It has to extract the data from the packet, then it has to deliver the data to the above layer. Okay, and it has to send an acknowledgement to the sender that the data has been received correctly. Once this is done, it will again go to this same state, that is wait for call from below. Okay. This happened. Okay. Now see, both of them are in the corresponding states. Now let's see what happens if we have a corrupted packet scenario. Okay, so same thing from the sender side, you have, the sender is basically waiting for a call from the above layers. Now, when this event take place, that is RDT send data, then packet is created and sent over the medium. Okay, this is what is happening. Okay, now once data is sent, the sender will get into this state of wait for ACK or NAC, and correspondingly the data, when it is received at the receiver side, which is currently at this state, that is wait for call from below, what's the event that will take place? First, this will be checked that whether it is a corrupt packet or not. If it is a corrupt packet, then again the receiver will send a negative acknowledgement to the sender, right? So this event took place, and then a negative acknowledgement was sent to the sender side. Once that was done, the receiver will again wait for call from the below layer. That means the receiver will simply now wait for its only task, that is waiting for a packet to be received. Okay, what's the sender doing? The sender was waiting for an ACK or an ACK. So it receives a packet, it finds out that it is a negative acknowledgement packet. So that means it will resend the packet that it had already sent. Please remember that here the sender is sending a packet and then simply waiting to get the result from the receiver side. Okay, unless it is ensuring that the packet was actually delivered correctly, it will simply wait, right? So it will wait for either an ACK or an ACK, and it will correspondingly take step depending upon what has been received from the receiver side. Okay, great. Then it is sending the packet again to the receiver. Okay, again this will keep going on and on, right? So in this case, what is happening in the second time, suppose the packet was received correctly, so again, the same thing will happen. You have to extract data, deliver it to the layer above, and then send an acknowledgement to the sender side. Once the sender receives a acknowledgement that the data was received correctly at the receiver side, it will simply receive the packet and then get into the state. That means it will wait for another packet to be sent from the application layer side. So this is how your things will work in case of a corrupted packet scenario in RDT 2.0. Now, RDT 2.0 has a fatal flaw. Okay? Now, can anyone tell me what is a possible flaw that is remaining in case of RDT 2.0? You can take a look at the diagram here.
And guaranteed delivery.
You are guaranteeing that with acknowledgement that it was a correct packet, so that means the packet was
But
delivered only.
but if the packet was not received by the receiver, then it won't send it won't send an acknowledgement
Yes,
or a non-acknowledgement.
yes, yes. That is definitely one issue. Okay. Anything else? Any other
This
issue?
the same issue like if the receiver does not, while sending the ACK or NAC, if the packet is lost, then the sender will never know that the receiver has
Yes,
actually.
that is true. For both of you, this answer is true. But please remember that here we are dealing with an unreliable channel that only gives bit errors. It does not say that packet loss will be there. So that means it is saying that packet will be received, but it may be received as a corrupted packet. Only that will happen. Please see the previous slides. Okay, it's too far away.
Ma'am, what if the ACK or NAC itself is corrupted?
Exactly, that's where I was going. The ACK or NAC itself can get corrupted because the channel is having bit errors. Okay, channel can induce bit errors here. Okay, so let's get to that. Yes. Okay. So what happens if your ACK or NAC itself is corrupted? Okay. So you simply cannot. So the sender actually does not know that whether the receiver actually got the packet or got the correct packet or whatever packet it was received. If it is a NAC, it's fine. But if it is an ACK, whether it was actually a correct one or not. Okay. So what to do? So if the sender cannot simply just retransmit a packet, right? Otherwise, you are simply sending duplicate packets to the receiver side. Okay, that is also a loss of resources or wastage of resources that you simply sending duplicate packets over the channel. Now, if you have duplicates somehow, then how to ensure that the duplicacy is taken care of or handled? Okay, so what will the sender do? That the sender will retransmit the correct packet if it finds out that the ACK or NAC is corrupted. Okay. So what does the sender do? The sender simply adds a sequence number to each packet. Okay. Now, if the receiver, finds that it is a duplicate packet, that is whatever it had received was the same sequence number, so it simply does not deliver the packet to the above layers. Okay, why to waste all this processing on that, right? It simply discards the packet. So this is how duplicate packets are, handled in this case. So again, this is also a stop and wait protocol. The sender will send one packet and then it will wait for the receiver's response. Okay. So let's see in the RDT 2.0, if we have erroneous ACK and NAC packets, then how things will work. Okay. So this protocol is called as RDT 2.1. Okay. And we are currently looking at just the sender side. Okay. Now please remember that we are adding sequence numbers to the packet so that duplicates can be handled. All right. So let's see. So we have 4 states here for the sender to move. Now the first one is wait for, so call 0 from above. So we have numbered the packets as just 0 and 1. Okay. Alright, so this is just for some simplicity. So you can simply have 0 and 1 just to know that whether the packet that was sent that has been received or not, and then what are the corresponding sequence of events that can happen. Okay, so there are only these four set of states that the sender can move to. Okay. So wait for call 0 from above. So now what we are doing, so this is the event, that is the data is being sent from the application layer. What is the action being taken? You make the packet with the corresponding sequence number. In this case, we are just, this is an example. So we are taking sequence number as 0, the data, and of course the checksum, and then send the packet over to the medium. After it sends a packet, then the sender will wait. It will wait for the acknowledgement or the negative acknowledgement for this packet number 0. Okay, so that's the state where it is moving to. Now what will happen? Now once it receives a packet, okay, it will check that whether the packet is corrupt or not, whether and if it is an ACK packet or not. Now if this is true, that means the received packet is not corrupt and it is an acknowledgement, sorry, the received packet is an acknowledgement packet and it is not a corrupt acknowledgement packet. So what it will do, it does not have to take any action, it will simply move to the next state. That means it will wait for next sequence, next packet, okay, packet with next sequence number that has to be sent from the application layer side. Okay. So this is what the state is now. All right. Now, once it goes to this state, then again it will wait for a call from above. Once that happens, a packet with the next sequence number, that is 1, and data checksum, they are added, the packet is created, and then it is sent over the medium. Okay. Once that is done, again it moves to this next state, that is it will wait for acknowledgement or negative acknowledgement for this corresponding packet with sequence number 1. Okay. Once it receives an acknowledgement for this sequence number, that is sequence number 1, if it is not a corrupted acknowledgement, then it will simply move to the next sequence number. That is, we are only considering 0 and 1 as a sequence number right now. So wait for call 0 from above. Okay. So this is how it will happen if everything goes well. All right. Now let's see if things do not go well. Okay, that means you actually receive a NAC packet or the NAC packet is actually a corrupt NAC packet. Okay, so you have received, so let's check at this point. Okay, that is your sender has sent the packet with sequence number 0 and it is waiting for an ACK or NAC for this same sequence number. Okay. So what it will do, once it receives a packet, it will check that whether it is a correct packet or not, or it is a negative acknowledgement or not. Okay, whether the negative acknowledgement is a correct packet or not, or it is simply a negative acknowledgement packet or not. Okay. So in these cases, the simple task that the sender would do is that it will simply resend the packet, and that's what it is doing here. Okay. Again, once it resends the packet, it will simply wait in this state. Okay, and this will go on until it receives an ACK. Okay, a non-corrupt ACK packet. The same thing will go on in this case also, where the sender is waiting for ACK or NAC for packet with sequence number 1. Okay, if it receives a NAC or the NAC is a corrupted one, then in this case, it will simply resend the packet and wait for again an ACK or NAC. Okay, so basically, the sender is sending a packet with a given sequence number, then it is stopping or waiting until it receives a response from the receiver side. Okay, now if the received response is correct, only then it moves on to send another packet. Otherwise, it will resend the packet and then again stay in the same state. That means it will wait for a response again from the receiver side. All right. So this is what is going to happen in RDT 2.1 at the sender side. Now let's check at the receiver side. Okay, so we are dealing with packets with sequence number 0 and 1. Okay, so two states will be there for the receiver side. One is it will wait for packet with sequence number 0 from below, and another is packet with sequence number 1. Okay, so let's see. At first, initially it is at this state, that is wait for packet with sequence number 0 from below. Okay, now once the event occurs, that is the receiver has received a packet and it is not a corrupt packet and it also has the correct sequence number. Okay, so data needs to be extracted, and you found out that it is the checksum matches and the sequence is also correct. So that means packet will be sent to the above layers now. So what are the tasks that need to be done on that? You extract the data, you deliver the data to the above layer, and you send an ACK packet. But now in the ACK packets case also you need to send a checksum because you want to ensure that the ACK is not a garbled ACK. Alright. So this is how you send an ACK packet with checksum and then just send this packet over the medium. Okay. Now once you send the packet, that means you are now ready to get the next packet which is in order, which is packet number 1. Okay. So while this is being done, please think of the scenario that if you have, we basically divide a data into small messages and then we transfer it over the medium, right? That's what we have studied until now. So just take a look at the case and think from, this example. You can think any other example with any sequence number of packets, and then you will see that how in order delivery can be done. Okay, that means you are the receiver at the end is basically going to reassemble all the packets that it has received in sequence, right? So yeah, at this point it is waiting for call from below for packet with sequence number 1. Now, after that, what happens? This event takes place. That means it has received a non-corrupt packet with correct sequence number. Therefore, it will extract the data, deliver the data to the above layer, send an ACK with checksum, and then send the packet over the medium, and goes to this state where it will wait for the next packet in sequence, and the next packet in sequence is packet with sequence 0. Okay. Now, if it is a corrupt packet, now we'll get to the scenario where we have, corrupted received packets. So, if the packet that has been received at the receiver side is actually a corrupt packet, then we know that it will send a negative acknowledgement. But now, because we can have garbled ACKs or NACKs, a checksum has to be added with that. Okay, so a checksum is being added, and then the packet will be sent over the medium. It will still remain in this same state until it receives a non-corrupt packet. Okay. Now, there can be another case also. Why? Because duplicate packets can also occur. We have already seen that, right? That if the sender mistakenly sends the same sequence number packet more than once, so then what will happen? So in that case, see, if you have received a packet and it is not a correct packet, but it is not the sequence number for which the receiver is actually waiting for. The receiver is waiting for packet with sequence number 1, but it has received packet with sequence number 0. So it is of no use, because you know that packet with sequence number 0 has already been extracted and transferred in the previous action, right? So this packet will not be sent further to the above layers, but what is the action that it will take? It has to tell the sender that you are actually sending me duplicate packets, right? So what the receiver will do, it will simply make an acknowledgement packet with the corresponding checksum, okay, and then it will send that packet. So the acknowledgement is for packet number 0, right? So it will simply send this acknowledgement packet and it will inform the sender that I am receiving this acknowledgement packet with sequence number 0. Okay. Uh, So this is the same thing that will happen if it is in this state. Okay. So if it receives a correct packet and not a correct packet and it has a different sequence number, so in that case, or in this side also, at this one, that is wait for 0 from below, there an ACK will be prepared with a checksum with the corresponding sequence number and it will be sent to the sender's side. Okay. And of course, if a correct packet is received, then there's no other way around. A negative acknowledgement has to be sent with the corresponding checksum and it has to be sent to the sender. Okay, so this is basically RDT 2.1 sender side and receiver side. Okay, now if you have any questions, you can ask me because time is up for the class. So please go ahead and ask questions if you have. Um, Otherwise, yeah, I can see anyways that yeah, uh, please go ahead and ask questions if you want.
Since there are only two possibilities, ACK and ACK, if the ACK